So, we have already formulated the Stokes equation. So, now we will look at the stream function wave theory. And so, Stokes gives us this for nonlinear waves. So, when you analyze offshore structures, you look into the diagram that I have given, that is the applicability of all the theories. Do not blindly apply your linear wave theory. Now, in the Stokes wave theory, I told you that you can split up into the first and second and the number of harmonics. So, you will get this kind of equation from the nonlinear Bernoulli's equation or the other non-linearities that is present. So, here I am just giving you the glimpse of what you have to do. So, this is coming like this. Now, the problem that will come is in shallow water. So, 4, this is sine hyperbolic cube. So, this is your second order term, and this actually it consists of the first and second harmonic. Why harmonic? You can see the second term is having a cos. So, this is your cos hyperbolic 2 k d, and this is cos of this is twice omega t, isn't it? Twice of omega t minus k x. So, that means your phase angle is the same. Now, here actually this is your first harmonic and this is your second harmonic, but you can split this up into as many harmonics you like. So, here actually the Stokes wave, it consists of two waves. There is the first is your linear wave and the other is your second harmonic, having the same phase angle. So, similarly you can go on doing this, and your epsilon is this is A multiplied by the k. K is your wave number and A is the amplitude of the linear wave. Now, here what you do, you can keep on doing this. Say your third harmonic will be epsilon like this, etc., plus epsilon square. This is eta 2 x. This is what I have written, x t plus. So, like this you can go on. Now, each iteration actually consists of putting the first two terms of the previous terms into your nonlinear equation, or especially the Bernoulli's equation. So, you will get the higher order terms. So, here actually the higher order terms obtained from previous terms. So, this is the essence of Stokes theory, but by this method actually you will find, if you do a computer program, your Stokes theory takes a lot of computer time. So, Stokes is actually more complicated. And in offshore, actually offshore normally we employ we go for Stokes second order or fifth order. Sometimes you also go for fifth order term. So, this the regime of application I have given you in the previous diagram. So, I am not going. So, in the diagram actually you also have Stokes second, third and fifth order terms. So, after the linear, then Stokes, then you have sinusoidal and solitary waves. Now, here what you do, so you can see in these Stokes there are a number of waves composed of different nonlinear terms. Now, Dean further said that when there is shallow water, it is Stokes equations are more complicated. So this is called Dean's theory. Dean's theory for shallow water. Now, in this theory actually you do not use the velocity potential. So, phi velocity potential now what is the meaning of this term velocity potential? So, that means the differentiation of phi will give you the velocity, isn't it? So, velocity potential is replaced by another term by psi. This is called stream function. Now, here actually the problem has come from applicability of Stokes theory, because Stokes theory will take up a large computer time. As you can see, you can go the previous iterations will give you the next term, but here actually at one go you can do, but prior to that you have to define what is called this stream function. And a stream function is defined in such a way that you can get the velocity potential. Now, stream function you can apply only for the two-dimensional case. So, that is the limitation. Say here you apply it say in the vertical xz plane. Say in this plane you can apply it. Say this is your x plane and this is your z axis. So, in this plane if you apply, then you can get your velocity, that is your del psi del z, del psi over del z. So, that will be equal to your velocity in the x direction. Followed. Now, what is the velocity in this x direction? So, this is nothing but del phi over del x. Similarly, we have minus. Now, here actually the minus term is given for a definite reason which we will see just now. So, minus del phi over del x. So, that will be equal to u z, velocity in the z direction. So, this is equal to del phi over del z. So, this is the definition of a stream function. So, that means if you plot del phi over del z, if you plot a stream function, say this is your stream function, you plot, actually you have to plot, sorry, this is xz plane. Suppose on the horizontal xz plane, you have to, there are three axes. If you plot, this is your psi axis, then you have, see this is your x axis and this is your z axis. Then let us say what you will get. So, you will get a three-dimensional curve. Now, you look at these two equations. So, this is equation number 1 and equation number 2. Forward. So, you differentiate this with respect to z. So, actually you will be getting a contour, that is you will be getting a So, this is no more a one dimensional curve, you get a surface like this. Now, what is the meaning of this del phi over del z? Or rather you can look at this del phi over del x. So, that means you take from this curve a straight line and say this is your del phi and this distance is del x. So, this is actually the slope of the psi surface. So, what we are getting is the slope of the psi surface. So, here actually you will get the velocity. Now, velocity will be in what direction? You find out the slope from here, from the psi surface contour, and slope you will get the velocity not in this direction. Now, the z direction is going inside the blackboard. So, we will get in the opposite direction. So, this actually gives us both the magnitude and also the direction. So, actually you have to plot a psi surface with respect to x and z. So, now you do the other term, that is with respect to del psi del z, but that will give you velocity in the x direction. So, this is the gist of the psi function. Now, the reason that we have taken del psi del s and minus del psi del x is it should satisfy some fundamental equation. What? Satisfy the equation of continuity. That is why this formulation you will find del psi over del s and minus del x del x. Now, it means the psi equations. So, here you write your stream function. Now, what is your equation of continuity? So, equation of continuity in 2 dimensions. So, equation of continuity in 2 dimensions, you write the equation of continuity. So, this is del ux over del x plus x and z plane. So, we are getting plus del u del z. Now, you find out the value of this. And see whether this satisfies your equation of continuity or not. So, what is your ux value? Ux is del psi over del z. So, this will be how much? Del psi over del x del z. And similarly, you write the other term. So, this will be minus, that is why we have given the minus sign. So, this will be del z, isn't it? U z was this is del psi over del z. Sorry, this I think this will be del x is del psi over ux is ux we are getting by del psi over del z. Sorry, this is your del z. So there is a mistake actually. This will be del z. And this will be how much? Del square here. So what will be this? Same thing, isn't it? So this is equal to 0. So that means this satisfies your equation of continuity. So that is why we have written del psi del z equal to ux and this one equal to uz. Now, with this you formulate this stream function. Now, actually here also you split into number of wavelengths or number of harmonics, that is split ocean wave into number of harmonics with stream function. But here actually instead of, you will find in the Stokes example, that is, it is a sort of iterative example, isn't it? But here actually in one shot you can find out the nonlinear terms. So advantage is get nonlinear waves at one go. Now here this for shallow water we have to make certain corrections. For shallow water you write this epsilon is equals to the amplitude of the harmonic wave multiplied by the wave number k. So previously this we had done this, isn't it? Epsilon is equal to a k, but this has to be modified. Modified to this beta a divided by d. You bring another term d. So here a term d, that is depth of water, is brought into the equation. So this is what you have to modify, that's all. So now the surface elevation, so that means you can see that the ocean waves are not sinusoidal waves. Then you write surface elevation equation. Surface elevation in terms of beta. So this will be, so previously we had written in terms of epsilon, so now you write this in terms of beta. So these are your nonlinear harmonics. So like this you can go on. Up to third harmonic I have given. Now in this case you will find this, of course these are called sinusoidal waves. So I said this is not harmonic. Sorry, you will not get a harmonic term as in the Stokes. So you will get sinusoidal waves like this. Now here this sinusoidal wave will come as a certain hill of water. So, you can see the ocean waves are somewhat like this. That means, when you are coming towards the coast. So, this is called sinusoidal. So, this is your surface elevation eta, and the horizontal axis can be time or space, whichever you can like. Now, suppose this depth becomes equal to 0 or very, very small. For very small depths, this L by D will tend to infinity. Now, in this case, wavelength becomes very large. And you get a wave profile like this. So, actually when you are coming towards the coast from deep water to shallow water, the water actually piles up. As you can see from this is your mean sea level. So, this is your mean sea level. So, the amplitude of the wave is largely above the mean sea level. The mean sea level actually also can come down here. So, this wave is called the wavelength is very large. So, another peak you will get somewhere here, which I have not drawn. So, here you say that this is a solitary wave. So, it is quite interesting, huh? Or sometimes this is called a soliton. So, this picture we are getting when you are coming from deep water to shallow water. So, from deep to shallow water. So, that means in the shallow water our problems are more complicated, isn't it? Deep water actually you can go for the linear wave theory. But your linear wave theory does not hold good for coastal waters, as we can see from this diagram. So, actually I think we do not have much time in your hydrodynamics class. You try to derive these equations for the sinusoidal and solitary waves. So, this is I wanted to give you the picture of the wave profile. Now, there is another important theory which is called the wave spectrum. So, all of you are doing my vibration class. So, waves and spectrum are analogous to your vibration. Wave is nothing but a vibration, it is disturbance of the surface profile by giving some energy, wave spectrum. So, in ocean engineering you come across this word spectrum. Now, spectrum actually gives you the wave energy at a particular location. Spectrum gives information on what? On energy density. At a particular location on the sea surface. Now, how you have derived the spectrum? So, spectrum is always derived spectrum derived from what is called wave records. So, along the on the sea surface or along the coast, particularly everywhere, you will find wave data buoys or data buoys. So, these will tell you the surface elevation. Surface elevation of waves. At a particular time. So, if you want to make your spectrum, so that you have to get data from wave buoys. So, wave buoys you will find on the sea, and they transmit data to the shore at specific time intervals. So, you record your surface elevation. Now, what you will get is not a simple harmonic wave, but you will get a wave record like this. So, this actually, but how to analyze this kind of wave record? So, this is a random signal, isn't it? In vibration, we call wave as a signal. So, this is a random wave. So, this is what you are getting from the wave buoy. With respect to time, you are getting a surface elevation. But can you make any analysis from this? So, this is called a so those of you who are studying vibration, this random wave comes under random vibration. So, this is say now the wave buoy is actually giving you the surface elevation for a certain duration of time. Say you call this d. So, d you denote as time duration. Now what is done actually, you have to split this up. So, split, or rather surface elevation into number of harmonics. So, either you can split this up as a sine wave or a cosine wave. Or now, how the picture is going to look like? Suppose this is your surface, a random you have got for say time, duration of time, maybe 1 day or 12 hours or 1 hour, 2 hours, whatever it is, you have got the surface elevations. So, these are your eta values. Now, some scientific analysis has to be done, isn't it? So, this is your means, this is your, from your mean sea level you are getting this. Now, if you want to do this, you split this up into say a harmonic components, but your harmonic components are going to have many frequencies, but there should be some definite methodology by which you do this. So, our main intention is to get information from this kind of a random signal. So, waves, if you study, actually you are studying signal processing. You have to do a lot of signal processing in order to get the required information. So, now you will find that this is say your mean sea level. You can have your first harmonic, say this is one wavelength, then you can have a number of wavelengths, but the result of all these harmonics will give you this elevation. It has to give you this surface elevation. Suppose you are splitting up all these harmonics in some arbitrary fashion, and then at the end you do not get the surface elevation profile. So, this is your surface elevation profile. So, this is very important, because you are straight away you are getting this from, so surface elevation profile from wave records. So, like this you split this into number of components. So, this actually should give you, generate this surface profile. If it does not generate, then you have to alter the parameters of your harmonic components. It can generate or it may not generate. So, nowadays there are complex computer programs to solve your problem. So, instantly you will get the wave spectra with which we are interested. So, you are getting this. So, this is summation. So, you are getting from here to this. Now, the equation that you will apply is a what is called a Fourier equation. So, in your maths class you must have come across what is called a Fourier analysis. Fourier analysis to be done on wave record. So, this particular thing actually you study in dynamical oceanography, and ultimately you have to get eta t, that is this curve, followed from what? From number of harmonic components. So, you write your equation in this form. So, this is in fact a Fourier series. So, this is what you should get, but you have to derive what? You have to find out A is, the small a is the amplitude of a harmonic, not your surface elevation. This is amplitude of a harmonic. Harmonic is other harmonic, you give you a sine curve or a cosine curve. So, this is the amplitude of a harmonic. What is your frequency? Achha, this is not F1, you write this as Fi. So, your harmonic will have a certain frequency, and what else? And it should have a phase angle. This you should know. These three terms out here, that is AI is your amplitude, Fi is your frequency, and alpha is the phase angle. Now, Fi you write this as I over d. Now, d has already been defined as, what is d? This is time duration. Now, we are getting number of frequencies from this time duration according to the values of I. Now, I you can give 1, 2, 3 like these values. So, if you give 1, 2, 3, then what is your frequency interval? Frequency interval is delta f, and how much is that? So, delta f will always be the difference between 1 and 2. So, this you will always get this as 1 by d. So, here we are getting from the wave record number of frequencies. So, that is the number of frequencies of your harmonics. So, now what you do, you in this equation you have to find these are called the Fourier coefficients, this AI and alpha I. So, AI is called a Fourier coefficient. You have to find this out from wave records. Now, the interesting part in the analysis, you will find that you will get this kind of variation in the amplitude. So, this is the fundamental wave record that we have got. So, this is a random surface elevation. So, we are getting something like this. Third, of course, this is not decreasing. Now, this there will be two graphs you will find. One will come for amplitude, which we will shortly see that it is following a definite distribution. This is your amplitude profile will come A. So, rather you can write AI. Now, what you are doing is plotting some discrete frequency values. So, you will get discrete values at particular frequencies. Now, later on you will find that this is called a what type of distribution. So, like this it will go on. So, these are your frequencies, or rather you can write this as frequency interval. So, this is 1 by d. The horizontal axis will be frequency Fi. AI is your amplitude. Now, from this you will get this distribution, and you will also get a phase distribution. Now, you have to have to get the values of AI and alpha I, otherwise you cannot get your surface profile. Now, I is for a particular frequency. Now, your phase distribution, you will find that this is not a, this is actually a logarithmic curve. Now, here actually you will get a phase distribution like this, somewhat uniform, but not exactly uniform. And this also will be on the other side of your axis. So, this is your, again this is your frequency. Your horizontal axis is frequency, vertical axis is what? This phase. Now, this AI and alpha I you have to obtain from wave records. So, this actually closely follows what you will find. This is called a Rayleigh distribution. Now, the phase angle alpha is your phase angle. So, AI is actually your amplitude for harmonics. With different frequencies, it follows what is called a Rayleigh distribution. So, these are all log normal distributions. But you will find, surprisingly, you find this angle alpha I. This is your phase angle. This is rather a uniform distribution. Now, actually, if you want to have the spectrum you have to get for number of wave records. The reason is that your wave elevations are random. So, you take wave records the same time duration at a particular time of the day, say for a consequent say 4 days, 5 days, 7 days at a particular location, but you will find that you are not having the same elevation. These elevations will be different for different time records. So, that means we are getting a random wave history or random elevation. Covered. Now, what is to be done is, if you do a spectral analysis, you have to find out the mean of a particular frequency, mean elevation for a particular frequency from all these records. Say you have taken M records. So, M is experiment has been done many times. So, you have to have the average value, M equals to 1 to M. Now, this is done AI for a particular frequency. So, this I is for a particular frequency you do, and then you do this, obtain values for all frequencies. So, how this is done? So, you will obtain. So, I told you this surface elevation you split into number of harmonics, but that will give you for one particular record which you have obtained. Say first harmonic for one record you have got, then the next day also you do the same experiment. So, the experiment is repeated, M equals to 1 to M number of times, then you take the average value. So, this is giving you the average surface elevation. Now, what is done is, instead of taking the elevation, you take the variance of the elevation. So, elevation of the surface by itself does not convey any physical meaning. Does not have any physical meaning. Why? Because you will find that if you take sum of the amplitudes and the mean of the sum, they are not the same, they are not having equal. So, what you do is, you go for square of the amplitude. Why? Because the square of the amplitude you will find is directly proportional to the total energy of the wave. Total energy of the wave is combined of two parts. One is your potential energy plus kinetic energy. This is the total energy of the wave. So, what is the formula for potential energy? So, I think this is 1/4, and you look up this, and total energy will be half of the square of the amplitude. Bar means I have taken the mean value. So, this is actually the total energy. So, this has some physical meaning rather than the simply your amplitude plotting. So, what we are getting, but these are what in the graph that you have plotted is only for discrete values. So, graph that has been plotted for discrete values of frequency. Now, here you decrease the frequency range or frequency interval, then you get a continuous function. So, in the limit you take delta f tending to 0, and this will be half of delta f, sorry, no, 1 by delta f and half of the amplitude square. So, this is a continuous function instead of a discrete function. So, today we will stop here. Now, the next class we will have a look at what type of the frequency spectrum we are getting.